Hello and welcome to the final week of Structures 2. This week we will be discussing our final two structural materials, wood and masonry. Due to time constraints, this discussion will not be as in-depth as previous discussions on concrete and steel. I've done my very best to narrow down the most essential topics, but note that there are still more things that you may need to know. Being an architect or an engineer means that you will essentially always be learning. There is just so much out there to know about what we do, and it's impossible to fit it all into an 8-week course or even a multi-year degree, and that's why continuing education is so important in our profession. With that said, let's move on to our next structural material, wood, and let's look at some advantages and disadvantages. Of course, the major advantage here is that wood is currently the only renewable and sustainable structural material. If you want to have an immediate, drastic impact on the sustainability of a project, you should consider wood as a structural material. Next, wood has a fairly moderate strength-to-weight ratio. Like steel, it also has both compressive and tensile capacity, which means we can use it in applications that transmit tensile forces without need for reinforcement. I've listed here an approximate range of compressive and tensile capacities. You may notice that this range is quite large, and that's of course because there are many different types of wood as well as different grades. And it may surprise you to learn that wood is actually typically graded visually. So unlike steel and concrete, which undergo testing to determine their grading or capacities, wood is graded based solely on appearance. A person will pick up a piece of timber, count the number of knots or deficiencies they see in the wood, check to see if the member is straight or not, and they will determine, based on that visual inspection, what grade they will assign that piece of lumber. And they do this very, very quickly. This leads into our first disadvantage of wood. Wood is a heterogeneous and orthotropic material. Those words probably mean absolutely nothing to you right now, so let's first define their opposites. A homogeneous material is uniform in composition and therefore has the same properties throughout. In other words, if you took a large piece of a homogeneous material and cut it in half, both new pieces would have the exact same properties as one another. On the other hand, for a heterogeneous material, such as a wooden log, if you were to chop that wooden log in half, you may find that one half of the log is stronger than the other half. Again, depending on the number of knots or deficiencies that either side has. Next, isotropic materials have the same properties in all directions. In other words, if you have a block of an isotropic material, such as concrete or steel, and you pull that material from top and bottom, the material would experience the same deformation as when you pulled it from the sides. Again, with wood, that is not true. And wood experiences very different amounts of deformation and has different strengths depending on how you pull or push on it. So let's look a little more closely at the composition of wood. And the analogy that I like to use for describing the structural composition of wood is this. Imagine holding a bundle of straws that you have dipped in glue. In this analogy, the straws are cellulose, and the glue between the straws is lignin. Now, you can imagine that if you pulled or pushed on this bundle along the length of the straws, you would probably be able to apply a decent amount of force. However, if you pulled or pushed the straws from the sides, they would easily come apart or squish together. The same is true for wood. Wood is significantly stronger when forces are applied parallel to the grain versus perpendicular to the grain. Also, if you imagine dropping a knife between the straws, that knife is going to slide very easily through the straws and break apart the glue. And that's, of course, why we chop firewood like this. On the disadvantages side, there are many things that like to eat wood, including bacteria and insects. So wood has a very low environmental resistivity. However, there are ways that we can treat the wood so that it lasts longer. One method is by burning or charring the wood, and that charred layer creates a protective barrier around the wood. This method is unfortunately not widely used in the United States, but it is very popular in Japan and parts of Scandinavia, and maybe it will eventually come over to the United States. Currently, in the US, we prefer using toxic chemicals to treat our wood in a process called pressure treating. Basically, we place the lumber in a chamber, spray chemicals onto the wood, and apply extreme pressures inside the chamber to drive the chemicals deep into the fibers. We can also cut small holes in the wood to drive those chemicals deeper, and that process is called incising. And you'll likely notice it on most utility poles all across the US. The next advantage may be a bit surprising to you. Large wood members actually do have natural resistance to fires. And that's because when a wood member catches fire, it starts to char. And that char eventually forms a protective insulative barrier, a lot like when we spray apply fireproofing to a steel member. So one method for ensuring proper performance of a wood structure in a fire scenario is to calculate the amount of char that will occur around the member, and then simply add that additional char thickness to your design dimensions. However, it's important to note that although wood does perform well structurally in a fire scenario, it is still a combustible material, meaning that it can catch fire and spread the fire as well as produce smoke. That distinction will come into play later on when we look at the International Building Code. Lastly, wood has a natural tendency to absorb and retain moisture due to its cell structure. Therefore, wood expands and contracts significantly based on the temperature and humidity of a space. You have probably experienced this yourself if you've ever noticed that your hardwood floor at home becomes more creaky during winter or summer, or if your door to your bedroom starts to stick during summer. Now let's move on to talking about different types of structural wood products. And here we have two basic types. We have sawn lumber, which are simply pieces of lumber that have been cut and dried, and we have engineered wood products, which are pieces of lumber that have been cut up and reoriented with the use of glue to improve structural properties. Within sawn lumber, we have boards, dimension lumber, and timbers. The important thing to note here with this chart is that when we discuss sawn lumber sizes, those are nominal sizes. So when the wood product shows up on site, the actual sizes are quite different. So for example, a 2x4 dimension lumber stud is actually 1.5 inches by 3.5 inches. A 2x4 is a lot easier to say than 1.5 by 3.5. Now let's quickly look at some basic types of engineered wood products. And the goal here is simply to learn some of the terminology for what you will typically see on a wood construction project. So first we have plywood, which consists of very thin wood veneers that have been laid out and glued together. Note that the direction of the grain alternates from layer to layer. So this top layer is going in this direction, the layer underneath will go the opposite direction, so on and so forth. This is done to make the product more isotropic, so that it has improved strength in more than just one direction. Next we have oriented strand board, which consists of smaller, thin wood shavings that have been thrown on top of one another and again compressed together with glue. As with plywood, orienting the wood in different directions like this makes it more isotropic. Next we have cross-laminated timber, which is the same basic idea as plywood but on a much larger scale. These are now full pieces of dimension lumber that have been laid and pressed together with glue. CLT can be used as load-bearing wall panels or as floor slabs, as shown in this image below. Next we have glue-laminated timber, or glue-lam. Here we have pieces of lumber that have been glued together to form a much larger section. The advantage to glue-lam and all engineered products over simply using a larger piece of solid wood is that we can control the material properties better. For example, a large 14-inch deep solid piece of timber may have knots or deficiencies in inconvenient locations for bending, either at top or bottom, as I've drawn here. So this knot would limit the bending capacity of this solid member. However, with glue-lam, we can cut out the pieces that are good and reorient them the way that we like. So again, in the case of a bending element, that means we may have select structural grade for the top and bottom two layers of timber, and then everything in the middle is number 2 grade lumber. This results in an overall much stronger and more efficient element. Glue-lam can be used to span much larger distances than conventional dimension lumber as beams or girders, such as in this image below, and glue-lam can also be used to span even further distances when used as an arch. And lastly, glue-lam can also be used as columns. Finally, we have wood I-joists, which consist of 2 sections of dimension lumber connected by a web of OSB. So those are just a few of the common engineered wood products that are available. And now let's move on to probably the most important topic for today, and that is on Chapter 6 of the IBC. Chapter 6, which is on types of construction, dictates the fire resistance requirements for various construction types. And whatever construction type you have will limit the type of occupancy you can have for your building, as well as how tall and how large you can build your building. And the important thing to note here is that whenever we use wood for any part of a building structure, we are immediately bumped to a type 3 or higher for the entire building. So having just one wood beam or one wood column in your building would immediately bump the entire building to a type 3 or higher, which could have significant impacts on the building occupancy, height, or area. And I'll leave it up to you to investigate further what that means by looking into the other chapters of the IBC on your own. So, to answer this question below, could we build a skyscraper with wood? Well, physically, yes, we could. But according to the code, no, we cannot. And that's because wood is a combustible material. It can catch and spread fire, and it produces smoke. Unfortunately, there's just no getting around that. But the code is actually starting to relax some of its restrictions on wood, just a bit. And now we do have some mid-rise heavy timber offices here in the United States. And by 2022, we could actually see even more mid-rise wood buildings when the next edition of the IBC releases. Now let's move on to sizing wood elements. And this discussion is not going to be nearly as in-depth as we saw with steel and concrete. Instead, I'm just going to give you some very rough builder's guidelines for basic column and joists for residential applications. So first, with columns, the basic rule is that we start with a 4x4 piece of timber when we're supporting just one roof or one floor, and then for each additional floor we add 2 inches, up to a roof and 3 floors. Beyond that, we likely would not be able to use timber anymore, and we would be using glulam. And note that the glulam sizes here are not increasing nearly as much as the solid timber sizes. And that's of course because the larger we get with a solid timber piece, the more chance there is of having deficiencies in that wood member. Whereas with glulam, we can continue to select the optimal pieces for our wood member that we want. Now moving on to the floor framing elements. Typically when we frame a wood floor, we space joists, which are just basically very closely spaced beams, at spacings of 12 inches, 16 inches, or 24 inches, depending on the loading. And the basic rule for sizing these dimensional lumber joists is based on the span. So a 2x8 can span up to 10 feet, a 2x10 will span 12 to 13 feet, and a 2x12 will span 14 to 15 feet. Note that we are not getting into the sizing of girders for this discussion. So those are the only 2 basic sizing guidelines that I'm going to give you for this course. If you want to know more about sizing wood elements, I would encourage you to look into purchasing this book. But for now, we're going to move on to our structural material performance matrix, and we're going to add wood to the discussion here. And the key things to note here are that wood does not typically perform well for large loads. Instead, we're looking at primarily residential or office space applications. We would not be designing, for example, a manufacturing facility out of wood. Wood can accomplish larger spans with engineered wood products like glulam, and the structural depth can be somewhat limited with products like CLT. However, wood is also a very bouncy material, and you have probably experienced that yourself in your own home or apartment. Wood does resist fire well, however, it is also a combustible material, and so there will be some limitations architecturally. And finally, wood does integrate well with other disciplines. It does allow for some architectural freedoms, and as we discussed earlier, it can be constructed very quickly. It will minimize the dead loads on foundation, and most importantly, it is by far the best product for minimizing embodied carbon. And so that concludes our discussion of wood for this course. In the next video, we will be talking about masonry, and that will be the final video for Structures 2.